a geologist for 50 years. She really doesn't look like a geologist for 50 years. She has 3 degrees in geoscience, the last one a doctorate from Colorado School of Mines, where she has been on the faculty part-time since 2000. She was also a geologist in the oil and gas industry between 1980 and 2015. Now and throughout her career, she is engaged with geology societies and boards. She is a past president of the Rocky Mountain Association of Geologists and thanks them for their opportunity to talk to you tonight. Currently, she is on 2 philanthropic foundation boards and is on the board of directors of Dinosaur Ridge. In the past 6 years, Donna pivoted to geoscience outreach, writing a book on the geology and mining history of Golden, Colorado, leading community field trips, giving talks to groups such as tonight, and discussing geoscience with middle and high school students. A fun fact about Donna is she never met a rock she didn't like. On the back table there is a sign that if you take a picture of the little square, it will give you access to a free ebook. Donna has also contributed a couple of door prizes for us, beautiful door prizes. So I hope everybody has a ticket. If not, we'll get you one after the program. Okay, please welcome Donna, Dr. Donna Anderson.
With fossils in them at the top of Mount Everest. And now we know from people who've gone up there, not just to climb the mountain, but to collect the rocks, that those fossils are, they had been deposited on the ocean floor. And so, how does that happen? Go ahead and advance the next one. So we also know now from lots of studies that those rocks are 464 million years old in a geologic time period called the Ordovician. And this is a map of what the world looked like 464 million years ago, which is totally unidentifiable. We have no frame of reference. The dot is where Mount Everest was at that time. It was way south of the equator, and it was in a tropical ocean, right about on the seafloor. So anyway, that's kind of bizarre. When I was just starting out, I go, like, no way, right? So how does this work? Well, that's what we're going to talk about tonight. So I felt that, this geology would be the most amazing thing because you could time travel. And that's kind of how that's turned out to be through my career. You can time travel through the rocks. And that, when we throw around millions and millions of years, that's what people come to call deep time. Very, very old time. Geology and astrophysics share that deep time concept. We'll talk a little bit about that. So to me, geology is history on steroids. That's great. So here's our ambitious roadmap. One of my colleagues said that this was an ambitious idea that I was trying to do with you all, so hopefully you'll stick with me. So we're going to do a little bit about the philosophy of deep time, reading rock layers, how do you do that, some examples, moving plates, because our continents have moved around over many hundreds of millions of years. How do you figure out what an ancient landscape looked like? And the climate throughout the last 500 million years. It's changed dramatically over that time period. And then we're going to get into what happened to Highlands Ranch right here. Where did we start 300 million years ago? I'm going to cut off 200 million years of time since the rocks in the basement here. The rocks above the basement rocks started about 300. So we'll just do that for tonight and come out to the month of August this year. So the deep time concept. Now that's a concept that has grown, it's kind of the history of science. over the last 200 years, people starting in England, France, and other parts of Europe started collecting fossils because they were really interesting. And they started documenting them and observing that certain fossils only occurred in certain rock layers. So they put them together in a column with the oldest on the bottom, and they found out that there were groups of fossils that would change as you kind of went up this geologic column in the subsurface of the Earth. And they started, instead of saying fossil XYZQR and then fossil ABCD, they assigned those names for time periods. So we have time period names like the Cambrian, Ordovician, Silurian, Devonian. And then we kind of group those into bigger time periods like the Paleozoic, the Mesozoic.
Mississippi.
The change to any one time period is where a group of fossils goes extinct. They don't occur anymore as you go up the section. There's two places, if you look on the left here with the big arrows, there's two places in the last 500 or so million years where there were gigantic extinctions, and we'll talk about both of those. One is at the boundary between the Paleozoic and Mesozoic, the lower arrow, a gigantic extinction. And then the one that you probably heard of, the Cretaceous-Tertiary boundary, is a big extinction. It wasn't quite as big as the older one. So we'll talk about this, but things really change at those boundaries in terms of fossils. So that's what marks the change over to these various main time periods. So then reading the rock layers, which happens to be my specialty in geology. I'm sure most of you have gone to the Grand Canyon or seen the Grand Canyon, and you know all the amazing rock layers there. Well, it turns out that there are similar rock types, like the red wall limestone. It occurs all the way through the canyon, east to west. It occurs up in Utah, it's all over the place. And in the Grand Canyon, they decided to name that rock formation the red wall. They gave it a name. It also has fossils in it. Oops. It has fossils in it that tell you the geologic time period. So we find out that the red wall limestone is Mississippian in age. Okay, fair enough. Where the rock layers change, sometimes there's a whole bunch of fossils missing, or other formations are missing. You go somewhere else and find those rocks, but not in the Grand Canyon. So that gap is called an unconformity. And there's various flavors. On the map, on the column here, there's at the bottom, there's the uncovered group that's tilted, and then it's overlaid by flat layers. That's a type of angular unconformity, where if something happened, it tilted up those layers, and then the stuff on top is flat. That's probably mountains that got built up and eroded down in the old times. Okay? So next. So on the side of the geologic column, you see all these numbers, and those are the actual dates. Now, this is not talking about high school social things. Dating is radiometric dating in this case. So since the 1940s, about the time of World War II, we have been able to date, radiometrically date rocks and figure out when those time boundaries were. So for example, the Cambrian, the bottom boundary is about 542 million years old. And that's all coming from age dates from unstable isotopes. So all you have to know is that these are the things that are radioactive, like radon gate gas in your basement is radioactive. Well, it's from decay of rocks that have certain elements like uranium going to lead or potassium going to argon. And these are changes in the atomic structure. It's very regular. You can figure out how long it takes to go from one to the other, and that's how you date the rocks. So it's pretty precise. It's gotten better and better over the last 80 years with better scientific techniques. So that's how we get those numbers. So then we have moving plates, the continents. Around 1912, the gentleman by the last name of Baker noticed that South America and Africa looked like they could fit together. And as it turned out, there were fossils, like little images of those little animals and then some plants, that went right across the Atlantic where that fit would be really good. India, Australia, and Antarctica, and realized they kind of all would have fit together too. Well, kind of fast forward, World War II, you had submarine warfare. Submarines were cruising around the Atlantic and Pacific Oceans, especially the Atlantic, and running into mountain ranges on the seafloor under like 3,000 to 4,000 feet of water. What was that about? So people started realizing that the crust was very dynamic. And we evolved from continental drift to what we now call plate tectonics. So the next slide, we're going to run a little movie, and we're going to see what happens between South America and Africa, and then some of the others. So we're going to see is what we call now the opening of the Atlantic Ocean, and see how those plates move. So here we go. South America's on the bottom right, left. Africa's on the right. And so you can see the United States and Africa are splitting first, and then finally it splits down to Africa and South America. At the same time on this side, there's a purple line where there's little bars. That's where one plate's going under another. That's the Andes Mountains today. So when the plates shift and spread apart, somewhere else a plate has to get overridden. And that's where you build mountain ranges. So the idea of a good fit with some fossils across the ocean in continental drift has now evolved to a very sophisticated understanding of how the crust has moved around, and you can date when it happened by looking at the fossils and the radiometric dates, etc. It's a very big connected story. Okay. So now we get to ancient landscapes. So we draw pictures of what the land might have looked at millions and millions of years ago. We try to visualize the Earth's surface at any given time. Our tools are fossils, sedimentary rocks, like the rock layers in the Grand Canyon, and stable isotopes, which are non-radioactive. And that's something that you and I have in our bodies, plants have in their cells, and then it gets locked in the rock when the organism dies, and or the rock gets deposited. So they're always there in an instant of time, and they get preserved from time forward. Really powerful. So we see fossils at the top left, that's a crinoid. We see petrified wood, that one happens to be a petrified national park with a petrified forest. And we know that crinoids live in the ocean. We know that trees live on the land surface, so there you have something about that ancient landscape right there. This is out near Rangeley, Colorado. It's a Raven Ridge outcrop on the lower left. And as you can see, some reddish-green shales transitioning these blocky layers. Well, that's going from a floodplain to a lake. You can see fossils of alligators and garfish and resistant beds, and in the shales you get to see plants that live on land. So you start to go, oh, we go land to lake, land and ocean. You can go a lot farther. On the lower right are the beautiful sandstone cliffs of Zion National Park with huge cross-fitting. Those formed in the ancient sand dune. So you can start to go, okay, that's what the land surface looked at when those rocks were formed. Okay. So then we get to a graph that's taken 50 plus years to be able to show this. And this is all based on these little stable isotopes that I discussed or mentioned. And you can find out, going back 500 million years, when the Earth was super hot, the red graph, and when it was super cold. And what that means is that when it was super cold, called icehouse climates, that was a world without polar ice, no ice in the poles. Today we do have ice in the poles. The hothouse has a world without polar ice caps, none, zero. And part of that evidence comes from stable isotopes, looking at many rocks and measuring that in the mass spectrometer in the lab, looking at fossils, looking at rocks. There's glacial deposits that tell you when the glaciers might have been. So this graph has evolved quite a bit over the last 50 years. This is probably the best rendition. But we see some real trends. We see some times when, wow, that red line is really prominent and long time. You can see the ice house, the blue, kind of wiggling around in the middle there. And you can see kind of where we are today at the far right side. So we're going to take all these things and go into the time machine for you. And I'm on the far side, so stuck with that. Okay, so let's peer into the time machine. Okay, and we're going to start with Red Rocks, or the Red Rocks Park, around 300 million years ago. And I want to just mention, red rocks are actually red because of rust. Just like a nail rusts when we put hair on it, that's what happens to rocks. We have little iron minerals in there, we expose it to the atmosphere, and voila, you have red rocks. So it's really simple why these are red. You see these all over the western US, you see these in New Jersey, you see them in Europe, it's red rocks that have basically rusted. So we'll start with red rocks at the foot of what we call an ancestral Rocky Mountains. And we were at sea level. It was a tropical climate. We were only like 5 degrees north of the equator, which is pretty close to the equator. Today we're at about 40 for your reference. And we were in an ice house climate. The green bar over there, we'll cap that graph, is kind of a little icon where we were. We're in a predominantly blue weekly lines in there, which means there was a lot of ice at the poles. There was glaciers melting and coming back, cycling around. So there's a lot of changes in sea level, because every time the ice melts, the sea level rises. So you see that in the rock record. That's, again, one of my specialties to do. So let's go to the next. So I'm going to show you a series of maps in here, courtesy of a really neat guy named Dr. Ron Blakey, who's been working on these renditions of what the world looked like at any time. He's been working on this for like 25 or 30 years. And so I'm going to be showing these little called paleogeographic maps. And the red dot will always be where we are right here. So for your reference. You can also see state boundaries. So you can see Colorado, Utah, Arizona, New Mexico. We'll kind of center on that. We see the West Coast over on the far left side. So at this time, right here, we were on the coastal plain near the foot of the mountains. There's what's called the ancestral Rocky Mountains, where the little lines are pointed. They were pretty high. Nobody knows exactly how high they were. They might have had some ice in them. They were high enough through glacial times. And we were kind of at the foot of that. The rest of the United States, if you flew over and onto an airplane, you would not recognize today. We have no good reference for that. But it was a lot of shallow seas and limestones being deposited. Where California is today, there was a little bit of a few mountain ranges, but the plains were kind of moving around a little bit and causing little linear mountain ranges to pop up. And that was the ancestral Rockies, which pretty much follow the Front Range today. It's the same place. So that was number one mountain range formed here that became the Rockies. So now I'm going to show you here's a rendition of what the Red Rocks time, the fountain formation, like at Red Rocks Park, Roxborough Park, would have looked like if you walked across the landscape. And on the right, the rocks are showing you, that was a river channel deposit where the label is on top, and you can see the arrow pointing to a curvy line. That's the bottom of a channel that carved into the underlying rock, and then it's a very coarse sand conglomerate on top, which means the rocks were deposited by very fast-flowing rivers. So we can do a rendition like this and look and decide, okay, there's some flat channels, there's some very odd-looking trees, because there were no actual trees like we know today, these were all ferns. So that's a rendition of what that looked like. And there's down at the bottom, there's an odd-looking animal that might have lived at the time. So you and there's the Rocky Mountains, the ancestral Rockies in the background. So if you took off the trees and put something modern you recognize, it probably would look super different from today. There were no grasses then, so you could add that in. Anyway, so the next rock layer that's everybody's probably heard of is the Lyons Formation, Lyons Sandstone. That's a very famous building stone in Denver. All those nice red flagstones that you see around town, and maybe in your backyard you have flagstone patios. That's made from the Lyons Sandstone, which is on top of the fountain in the Red Rocks formations. That was formed in a sand environment. So here you have a big dune field Again, you have some rivers flowing through it, some ferns. We find, this is a slab of sandstone we have at the Highlands Museum of Earth Science that has some little tiny footprints in it. These are called tetrapods, which is the technical term for a four-footed animal. Pretty nice word for a pretty simple thing. One of the guys that may have been cruising around out here was an early kind of reptilian with a big fin on the top called a megalodon. And so they were kind of walking around on the sand dunes looking for something to eat. Insects, I don't think insects were, yeah, insects were there. So that was kind of early insects, vegetation. So this is kind of the landscape of the Lion sandstone. And then the third rendition is a really austere-looking rendition of these little moundy things with ocean water around them. And this is the lake exploration, which is definitely not so famous. Nobody's probably heard of that in here. But the climate at this point got super hot. We started to go out of that glacial period, leave it. It got very hot and very mucky water, technical term for highly saline. And the only thing that could live in there are little lamination of fossil algae, which are shown there in the picture with the pencil point. Every one of those laminae, those little tiny lines, is a little mat of algae that died, and they got covered up, and then the next one kind of got on top. There's just probably 100 of those little lines in there. And they're like fossil algae. If you've ever been to Shark Bay, Australia, that would be a good analog for this. And those little mounty things are called stromatolites. They're a very interesting fossil. They generally reflect very severe ocean conditions. So what happened? Things got changed. Remember at that time I showed you about the change from the Paleozoic to the Mesozoic time period? At the end of the Paleozoic, at the end of those slimy rocks, we had a huge volcanic eruption sequence on the Earth's surface. We are here is about where we are right now. So this is what the whole continents would look like in the Lake Permian. And then right at the top of the red dots is a huge igneous province that people now think is what happened. It blew up so much stuff in the atmosphere. It polluted all the oceans. It ruined life on Earth. And it was the Great Dying at 252 million years ago. It was a massive extinction. 90% of all species in the ocean and on land were extinct. And, yeah, so it was, people now have kind of figured out from the geochemistry of a lot of sedimentary rocks that were deposited this time. There's a big nickel, other heavy metal kind of signature in those rocks, and that's why we think it's probably due to this massive volcanic eruption sequence up in the Siberian area, what today is the Siberian area. Otherwise, you wouldn't probably recognize the continents you flew over in there. So now we're going to go to the Mesozoic. After the Great Extinction, we had the breakup of the continents. The big mass you saw started to split up. Eventually the North Atlantic opened, the South Atlantic opened. The plates began moving out of the equator and northward, eventually, by the end of the Cretaceous, to about where we are today, at 38 degrees north. However, we were still in a tropical climate, or subtropical. And why is that? Because there was no polar ice, and we were in that green bar there, with mostly red, and the Earth was hot, very hot. It had a lot of carbon dioxide in the atmosphere. In fact, some people think up to 2,500 parts per million carbon dioxide, which you and I wouldn't like breathing. So it was a very different climate on Earth, and it was very, very hot. So it also brings us to the real Jurassic Park, which in the United States is this area kind of outlined in the green polygon. There's a Stegosaurus, our Colorado State fossil. There's an Allosaurus where the bones were first found at Dinosaur Ridge at Morrison. You can go see some of those bones on the field trip. And there was a huge inland area with rivers and lakes. It was kind of a savanna, but it wouldn't be like going to Africa. You wouldn't exactly recognize the plants, but you would see herds of dinosaurs out there. huge herds of dinosaurs. So it was the first kind of serenade for the United States. And that red dot is where we are today. And depending on the age of the dinosaur. I had to put this in here. I mean, this was great. This was a dinosaur national monument. And some wag just goes, you know, what about all the dinosaur pee? I mean, they were so big, and they, you know, there's a femur there. I think it was an allosaur, but that's the same leg bone that you have for your knee to your hip. But that thing is a human for scale. That thing was huge. These guys were huge animals. They had huge bodies. And one wag just could not resist about doing this thing about the volume of the dinosaur. We really filled a swimming pool, going on and on, so just bring that to your attention. But it was a savanna. It was fern trees and algae and lakes and ponds, and you had huge, that would be like a Apatosaurus in the background, running all over this massively large inland plain. So that was kind of the Morrison Formation, and that's one of the big formations you'll see on this ridge. So now we go to the Western Interior Seaway. We leave the Jurassic, and there's a movie running. You see the blue getting bigger and bigger, and we're in the middle. There was an ocean coming in from the Arctic. Then you have the Gulf of Mexico down in the lower corner on your lower right. And that sea kept connecting and shrinking and swelling over time, eventually getting really connected, getting really big, expanding, and we were underwater, folks. We were in the ocean. This is the Western Interior Seaway that dominated the Cretaceous period. At the end, the whole state of Colorado, most half of Utah, Nebraska, Kansas, north of South Dakota, most of Montana, half of Wyoming, most of New Mexico, all of Texas practically, was all a big ocean. So up to 1,000 feet deep. That's a debated number, but some people make that claim. That's why you can find oceanic marine fossils in Kansas, Colorado, Utah, blah, 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 et cetera, because we were under the ocean. Same latitude as today, about 38. Abundant sea life along the shorelines. You would get dinosaurs walking along the shorelines and made trackways. That's like at the other part of the east side of Dinosaur Ridge. It was a hot time. In fact, it was, the green bar shows you over there. Some people call it the Cretaceous hothouse. It was so hot. Which is not to say there wasn't rain, because it was probably kind of a monsoonal climate, you know, with seasonal huge amounts of water, rainfall. But it was very, very hot, and it was very, very tropical, cold. There was no polar ice at all. So here's two examples of the trackways. The one on the right is Dinosaur Ridge, where you'll go to on your field trip. The one on the left is Picket Wire, which is a very famous trackway down by La Junta, Colorado. It's in a riverbed, so you can walk on it and try to walk on it like a dinosaur. It's a lot of fun. They had really long legs. And in the middle is one of these renditions of what did that landscape look like. And now you have a tree on the right that you might recognize as kind of a ginkgo tree. You have lots of ferns, very tropical. You have bays and stuff along the shoreline, and some rivers running into the ocean. So it was a nice place for those dinosaurs to live. They were very prolific. And the other thing that happened is where there was not really a shoreline, you had a floodplain where you had swamps. And here on the floodplain deposit, when you had an excavation at Windcrest, there was a bunch of Triceratops bones found. This happens a lot around Denver. People will be excavating a foundation and dig up bones, and they will call the Denver Museum of Nature and Science out to do some work to preserve those. And this is the example of finding that at Windcrest a few years ago. And then in Golden, there's a Triceratops trail. It's a really nice example of a swamp. There's coal that used to be mined there, clay, and there's see in the shadow there, they were massively large palm trees. I take second graders out there and I go, do you see palm trees growing here today? And they go, no. Well, they don't. They need a much warmer, more moist climate, so it's a really different time here. So, of course, everything kind of has to come to some end at some point, and toward the end of the Cretaceous, around 70 million years ago, we had the second Rockies kind of rising up here. There was lots of plates running under the continent on the west coast, and mountains rising, and it transmitted into the interior more. Sea retreated, because as the plates and the mountains rose, the sea level would retreat, right? So we aren't at sea level anymore, so there's no sea. The second laterite mountains arose, and again, Highlands Ranch is at the foot of those mountains, the Red Dot. And then these.
That's cute.
We had an asteroid impact where the red arrow says impact here is on the Yucatan Peninsula of Mexico. And now that crater has been very well studied. It's been cored. It's an amazing amount of work that's been done. The people who understand impacts and blast structures can tell you that this comet came in from like the northeast at 66 degrees angle. They have figured it out to that amount of technical detail. And it's also really precisely dated at 66 million years plus and minus about 5,000 years with all the new dates that have come out. 75% of plant animal species became extinct, both land and ocean. Some people say 65. I'm not going to debate that. We are here at the top. We did not get the tsunami deposits that hit the ocean at the time. You can imagine a wall of water was 1,000 feet high. There was ejecta of rocks all over the place. We did get some layers of that here. There were tsunamis in the ocean. And most importantly, it caused forest fires. And it blanketed the earth in complete darkness for more than several years. Well, what does that do? Plants can't survive. Photosynthesis stops. Any animals that depend on those plants can't survive. So you had basically an ecosystem collapse when that happened. And this is Kirk Johnson. If you've been a member of the Denver Museum of Nature and Science, you'll know Kirk is a really famous plant paleontologist. He's now at the Smithsonian. But he took us on a field trip out to West Fiji Creek, out on the plains where this KT boundary is right at his finger. He's pointing to it. It's like about half an inch thick. So they did a bunch of detailed work, centimeter by centimeter, through these rocks, the column of his head was where he's pointing, and they found that a layer enriched in iridium, which is an element that only comes from space. And that is the layer of debris from the asteroid that when it hit the Earth, it threw all its rocks, and that's the little trace of what was left of the meteor, right in that little, where his fingers. There's only mammals above that, and dinosaurs only below it. That is the end of the dinosaurs, right on that finger. Wow. Except for birds. They made it through. Okay. Another excavation the Denver Museum has been working on actively for the last 6 or 8 years is down at Corral Bluffs near Colorado Springs in the open space. And there, the scientists there, Tyler Lyson, who's in the picture up on the top, have found amazing things, fossils, right after the impact. So it's just a little bit above that iridium layer. They found fossil turtles, crocodiles, garfish, and some of those skeletons are there in that lower picture. And there wasn't a lot of life, but I was amazed. They figured it took about 300,000 years, based on all their detailed work, for the ecosystems to really recover after the impact. That's quite a while, but in geologic terms, that's actually pretty fast. Yeah. By 64 million years, so you hit the asteroid at 66, by 64 million years, we were back to a tropical rainforest. And that's the rendition of the cute little mammal at the bottom. There's another excavation the Denver Museum did when I-25 was being reconstructed down here in the early 2000s, and Kirk Johnson was involved in this. CDOT uncovered a bunch of fossil leaves. It's basically the remnants of a rainforest. And there's a hand for scale, but some of those leaves are huge, which is real typical of tropical vegetation. So they did a lot of studies on that, and from those, they figured from the leaves and the comparison to more modern versions, the estimated mean annual temperature of that area, this area around us, was 72 degrees, which is a lot warmer than today's average if you take a whole year's average. And the mean annual rainfall was 88 inches. Like New Orleans. Yeah, I mean, that's impressive. So it really was different, and it wasn't that far above sea level. We were still, probably a couple hundred feet above sea level, but it was a tropical rainforest. So things warmed up again, and I call it the hot time of the Cenozoic, my Eocene time. Again, the green bar there, we warmed up significantly to a very hot time. The vegetation started changing. We had palm trees at the North Pole, the South Pole. There were large lakes filling big areas of southwestern Wyoming, around various parts of Utah, northeastern Utah, and northwestern Colorado. There were mammals everywhere. The first horses in North America kind of showed up, a little tiny. They were like no bigger than a dog. They were very tiny. And that was kind of what's called the Paleocene or Eocene thermal maximum. It's a very, very studied time of Earth's history. Again, carbon dioxide levels were very high, much higher than today, and the temperature was, averaging around 75 or 80 mean annual. It was pretty hot. So it was kind of like the next. I think a couple of you asked about that. At the same time of this general time, we had a big petrified forest all around here. But Cherokee Ranch, there's been a nice excavation down there of the petrified wood. This is taken from a scientific article. That wood is in the walls. We'll talk about the other side of the walls in just a minute. We have samples on the back table. There's a big log with a nice leaf standing next to it. So this is the age of the petrified forest at Cherokee Ranch and various other places around here. And the other rock that's in the walls at Cherokee Ranch and Tweed Kimball's mansion is rhyolite. It's an igneous rock. It's actually kind of a tuff, which is volcanic ash that is blown out of a volcano. People now figure that eruptive center was near Buena Vista and Mount Princeton. And it's kind of like, the idea of burying Pompeii with Mount Vesuvius erupting. Well, this was Mount Vesuvius on steroids. This was huge, and it buried this whole area around here, Castle Rock. It didn't quite, we don't know if it quite reached up to gold, and there's no evidence left, so we have a wild guess on that. But it was a very large area that got this tuff in it, and filled in all the valleys, and killed all the vegetation, and then one in front of that rendition of what it might look like as it was rolling down towards you, hotter than what. So that is what made the tuff. That is a big building stone all over Denver. So the castle at Cherokee Ranch is mostly made of that with some little pieces of petrified wood. A lot of the buildings in downtown Denver are made of a wall mountain tuff, and it's a very common rock and building stone in the front range. So then we had a lot of long period of erosion. The mountains wore down, the land surface wore down, but since it was a widespread savanna. Now this picture is a picture in the Kalahari Desert of Botswana. It is a desert. Look at all the grass. Look at the trees scattered around. That's what a savanna looks like. That is probably what this area looked like, different grasses and trees, but just kind of the scenery. And that's pretty much stuck around till today. So land just went down and created this really large flat plain. That's what we have here. And to the east. So you know this place? Yeah. That's Castle Rock. I'm talking about this erosion. Somewhere around Castle Rock, I just put a red line. That used to be the land surface. So everything below it has been eroded over a long period of time, leaving Castle Rock as a remnant. Probably, it took millions of years to get to today's surface, and where did the dirt go? It went to the Gulf of Mexico. Yeah, it filled up what's now known as the Gulf of Mexico. Because that place was sinking and the rivers were going out, just like the Mississippi does. The drainage just went out toward the Gulf of Mexico, and the eroded dirt went out and got deposited out there. And so we had the second American Serengeti, I'll call it. The first was Jurassic Park. The climate did start to cool off quite a bit, because we were actually starting to enter the glacial time we have today. We had lots of grasslands. There's the rendition, again. Think of that other picture from the Kalahari. Grasslands, scattered trees, grazers, predators. Basically, if you go on safari, you would do it in this time, and you see a lot of different animals, right? Like some things that brown sloths and huge bison and pigs, well, ancestors of pigs. The horses were getting bigger. So we had camels, yes, camels in North America. Pronghorn, or animal we call them, huge bison, brown sloth, rhinoceroses, elephants and relatives, many other animals on this plain right here in the Highlands Ranch area and in Wyoming, Colorado. So where our red dot is, you can see that it's kind of flat. Everything to the west is mountainous. There's huge mountain building going on over Utah all the way to California, forming the Basin Range of Nevada. But we stayed here in the American Serengeti, to the first. So the biggest change really occurred in the climate 2 million years ago. And that's when global cooling began to really start in earnest with that green bar. As you can see, that blue line really steeply diving off. So during that time of the last 2 million years, at times we had obviously ice at the poles. And sometimes that ice sheet covered the North Pole, all of Canada, the upper United States, and certainly a lot of Scandinavia and parts of Alaska. So it was huge. I mean, it was just solid ice. But that ice would melt and come back and melt and come back kind of cyclically over this 2 million years time. So now we have a really good record of what happened in about the last million years for Antarctic ice cores. So this data is taken from measuring gas bubbles trapped in the ice from Antarctica over the last 800,000 years. And so every time you see one of these little red spikes or pink spikes, that's a warming time. And all the blues are little cooling times. And those are ice ages. So you had warm, just over and over and over the last million plus years. And the temperature changed with that, of course, with the worldwide temperature and the carbon dioxide, which is also measured out of the same gas bubbles. The carbon dioxide shows similar patterns. That's it. And then we're in the last ice age, or actually the very last interglacial on the far right. And I want to talk about a couple of fossil deposits in the last interglacial and then bring it up to today. So, how many of you heard of the Snowmass big out there snowmass? Okay, so yeah, so that was another Denver museum. I guess I'll call it a salvage operation because an operator was digging a pond for repaying a reservoir, and all of a sudden, this is maybe 10 or 15 years ago now, found all these bones, like mammoth bones, and huge bones. So called the Denver Museum. it was like, oh my gosh, you guys got to come out here because we want to finish this up. We know it's important, and it was very important. This on the left side here, it's the deposits they found spanned the last interglacial, that pink spike, into the early part of the last ice age. That's the dating they got on that. It was an ancient lake filled between 140 and 55,000 years ago. They found thousands of bones, big and small, 50 species, at least 35 American mastodons, which is like an elephant relative, all genders and ages, insects, fossil woods with logs up to 30 feet long, but the species are real familiar. Fir, Douglas fir, spruce, pine, ponderosa, sagebrush, oak and juniper. Those are species we're all familiar with. So the species were the same, but in these two renditions, it kind of, the upper one shows like the warm time, there weren't any ice glaciers in the mountains around there. It looked pretty much like it does today. And then in the cooler times, they had glaciers and canyons. And there was some evidence that there was some glacial ice that was quite close to the pond. And there's a mastodon there, the shoreline, some ground sloths. So again, you had camels, I don't know if they found camels, but you had mastodons, bison, kind of the same species you find out on the savannah, but this was in a more alpine setting, so it was a very, very special thing. The last glacial period. So how much ice was there in the Colorado mountains? This is work that a friend of mine, Vince Matthews, who was our state geologist and now retired, has been working on this book, which I have cited, and it is. If you, 18,000 years ago, where that green bar is, you're still in what's called the maximum ice stage, or the last glacial maximum in the world. If you went up I-70 to Empire, and you tried to go to Idaho Springs, and you decided you wanted to go to Georgetown or Empire, you could not. It was a wall of ice. And there's actually some glacial deposits at the intersection where the two roads split. They're called moraines that kind of map to the maximum down valley extent of those two ice glaciers, basically. So there's our dot. I-70 is just to the west of that dot. And there's the blue shows the ice. So there's a lot of ice all over the mountains of Colorado. If you go hiking and enjoy alpine hiking, you can see lots and lots of glacial features. The beautiful cirques we see today when we go hiking, these were all carved in the last ice ages. Makes our beautiful scenery of the Rocky Mountains. Okay. So we'll go kind of fast forward, I guess, here, and we'll talk about really another famous place right near here called Land Spring. And this records a time after the last glacial maximum, after the ice had really melted out. And the green bar on the left is about 13,000 to 11,000 years ago. And that's the mammoth, camel, ground sloth, bison, bones that have been excavated out of the Land spring deposit, the pond deposit. So those were all the American savannas there maybe 13,000 years ago. The other thing that's also special about this was the Paleo-Indian human hunting that's been documented at that site that dates to about 7,500 years ago. And the fauna that they were hunting was essentially the same as bison, camel, mammoths, and ground sloths. So those animals were still surviving at least to 7,500 years ago in this area. They were cruising around on our, American Serengeti at the time, but they became extinct shortly thereafter. And the controversy has always been why did they could become extinct after humans showed up. I'll leave that to your imagination. Okay. And so here's what Land Spring looked like in 1961 when they first excavated it. And then here it was, I went out there because I thought it was so cool, and I have to credit one of the docents who was a former co-worker of mine, Betsy Keeley. She gave a really nice talk on this, so I got all of the right dates and stuff. But this is what it looks today. Here's what it looked like when they excavated in 1961. You can see some curved tusks here. Those would be the Columbian mammoths, which are pretty big animals. And then there's bison bones, and that's also where they found some of the human evidence of having cut the bones, which they did make a little bit younger in the excavation. So today I simply ended on this slide. So this is the end of the adventure. And you guys stuck with it pretty good, thank you. And as it kind of shows in this cartoon in your question, don't play with unknown dryers. So I have a lot of acknowledgements to make, many acknowledgements. Vince Matthews, the Blakey Deep Time Maps, Dinosaur Ridge colleagues, Bob Reynolds, who thought I was giving way too ambitious a talk for all of you because he thought I would need about 3 hours to go through it. Kermit Shields, Amy Atwater, Larry McCall, Kirk Johnson, who's now at the Smithsonian, James Hagedorn, who's a good colleague. I really thank the RMG Outreach Committee for, Sarah for asking us. Okay. And Bessie Keeley from Lance Spring and Roxborough Park. Apologies to Gary Washington. I will take some questions. Sure.
Raise your hand and I'll bring the mic back.
There's probably a million questions.
There's one.
Yes, there were so many times the animals were extinct, and then the next time they came back, different. How during this last period, we end up with animals here that are very similar to other parts of the world, like India, Afghanistan,
So I'll repeat the question. So with all the extinctions and animals coming back to how come we still end up with similar animals in in India, South Africa, or Africa? When you talk about elephants, India and South Asia have elephants. Africa has elephants, they're all different species. Elephants are gone in North America. There was a lot of migration when the glaciers melted, like the glaciers were maximum ice, sea level was 300 feet lower. That's a lot. And there were land bridges, there were definitely land bridges from Asia to North America. There was migration. That's probably what got things into North America. Plus, when the continents were drifting along around, there was times that they were all connected too, so that let the animals migrate all around. But mostly the sea level drop allowed that. And that's always been kind of they just migrated where they could. But why they disappeared here in 7,000 years ago or so, it's hard to explain without putting plenty of pressure on them. If you've ever, how many of you guys been to the Galapagos Islands? Isn't it amazing that you can walk up to animals and they don't even care? I mean, they don't recognize you as a predator. So when Paleo-Indians came into this area, and now there's really good documentation, they were here 20,000 years ago, and some of my Roxborough colleagues would say they've been here 30,000 years ago. But definitely, the animals had no clue that these people were predators. And you could literally walk up to them and kill them. So that's how I kind of think about it. It's like, it's kind of amazing to think that now. I do go on safari in Africa, I wouldn't have done that. Isn't it amazing you can drive in a car and a lion goes right next to you and doesn't care? I mean, you can touch them. We don't, but you part of the background, you're not anymore a hunter. So you kind of have to think in that regard that a few humans came into this herd that must have been like nirvana to them. You see all these animals out on this American Serengeti. They had great pickings for hunting. And I think there's some truth to the fact that hunting pressure causes the weak North America. But it's also true that the climate was changing radically. It was warming up. The grasses were getting, they had to evolve into something that could survive with less rainfall. So there was a lot of ecological pressure from the climate change going on as well as the human pressure. Is that kind of help answer? That was too much.
I have a question. This is a very fascinating subject. What I'm curious about is, do you have any idea at this point the changes that has happened on this planet? Has that been basically internal to the planet, or is it a combination of what's happening out in space and what's happening on the planet?
So right now, given our state of knowledge, both on the planet and in planetary geology, I'll call it, we just apply that it would be internal to the planet. However, it's not exactly with that asteroid impact at the KT boundary, we'll call it the KT boundary. So there are extraterrestrial things going on. If you look at, it's an interesting scientific story to read about the discovery of the KT boundary. It's a really good book that was written in the mid-90s by the gentleman who, and I can't remember the name, sorry, but defined the KT boundary. About the history of that, people rejected that. When they first came out with that in 1980, it's like, no way, not going to happen. Well, they kept going, they invented science to answer those questions. And I guess to me, that was part of that growing up too. I was like, oh, really? But then I saw an asteroid hit Jupiter. And you remember that? I mean, I'm convinced. These are long, low-frequency events, but they do come and cause great havoc to a planet like ours. So in that regard, there is there's out-planetary influence. Beyond that, I can't say.
Just a real quick question. You, in your presentation, you had illustrated different temperatures, average temperatures at various times. What's the average temperature right now throughout the whole world?
I'm not, I don't know. I should have looked that up. I know that the average carbon dioxide is 420 parts per million or so. And that contrasts greatly with the EC and some of the Cretaceous estimates of 2,500. But yeah, they don't, I have to say, I didn't look that up, maybe I could do that, I could Google it, and figure that out.
In 2006, Al Gore had a movie, An Inconvenient Truth, where he talked about how scared we should be of CO2. And your one graph of the CO2, it truly...
Takes a very shallow rise.
So that movie was not bumped then, because it was controversial movie at the time.
It is so controversial. I mean, there's controversy around it. I think as a scientist, I've seen so much evidence that that huge spike coming back up is actually real.
What was the size of the asteroid?
Yeah, that's actually, the asteroid was like 6 to 10 miles long.
So, you showed a picture where the horses were the size of the dogs. And I've recently learned that the horses that we have in this country came from Europe.
Yes. Oh, that's another cool story. The horses evolved on the North American continent, but they were gone. Just like the camels, the elephants, they were basically gone after about 7,000 or so years. And they had to be reintroduced when the Spanish came in the 1600s. They brought horses with them, and they repopulated their traditional habitat. Yeah.
So, how did the Rocky Mountains form? I understand that normally they form with boundary breaks.
Yeah, so
This
there's,
is the one happens in California.
yeah, so that's always been a fun thing to talk about, and there's been a lot more work on how understanding that, because it's easy to understand where a plate goes under another one, how that links to the local mountain stuff, but then how do you get it far in? And so what happened in the Cretaceous, and this is going on in South America days, in Bolivia, and then into Argentina. There's a place where the slab starts to flatten out. When that happens, it transmits stress way inland. And that is what happened in the Cretaceous that caused our laterite Rockies. Not only that, but reconstructing the seafloor with magnetic stripes. It looks like a huge oceanic plateau went down the subduction zone. It'd be like stuffing a turkey, just kind of putting more rock down there. And then that actually also made it flatten out. So that's what caused the laterite Rockies to come in so far in. And that's actually a pretty solid story.
You mentioned about the rhyolite and the petrified wood at Cherokee Ranch. There's also conglomerate that they use from the property. Is the conglomerate created from the oceans or anything significant?
So I have to say I haven't looked at that, but generally the conglomerate around here is a massive river deposit. A big floods. During the time of the Wall Mountain top, the climate was very monsoonal. There were many floods. And some of the floods are, the deposits that are left that are actually on Cherokee Ranch, I've seen those outcrops. They are like the biggest cross beds I've ever seen that aren't formed by a sand dune. Because let's put it this way. If you're ever in a sandstorm, the grains are really tiny, which is good. Because if they were like that big, you would be dead. So generally, wind doesn't pick up sediment that size. So if you see conglomerate in big cross beds, that's probably a river deposit, like 99% sure it is. And they are out of Cherokee, and they are some of the biggest flood deposits I've ever seen. And they're pretty solid, so I'm guessing that's where they came from locally.
Somebody asked about the average temperature.
Oh, the average surface temperature is around 59 degrees Fahrenheit. Thank you. Yes.